If you were asked to draw the solar system from memory, what would you draw? A big yellow circle in the middle of the page with 7 or 8 smaller circles orbiting around it. That's probably pretty close to how most people would answer this request. And if you were to ask an expert, they'd probably add some arrows to show the direction that these planets are moving and maybe color them appropriately as well. But that would still be a very inaccurate representation of our solar system. Let's start out by removing the planets from the solar system and focusing just on the sun. It doesn't have a solid surface like Earth does, so your drawing wouldn't even know where to start. As you descend into the sun, you'd first encounter extremely high temperatures and pressures. Eventually, things would get so hot and so compressed that the atoms present would become ionized, stripped of their electrons. This would turn the sun's core into a giant ball of plasma, which is partially why the sun shines. But there are 2 other reasons for why the sun shines. Let's go back to the beginning to explain the last one. The sun is about 4.6 billion years old, give or take a few 100 million years. It formed from a gigantic cloud of gas and dust that was slowly pulled together by gravity. As more and more material collapsed onto the center of the cloud, its gravity increased and increased until it was strong enough to overcome the outward pressure caused by the heat of all those collapsing bodies. Once the collapse was complete and the sun was born, nuclear fusion began in its core. Hydrogen atoms were forced together under extreme pressure and temperature, turning into helium and giving off energy in the process. This energy, primarily in the form of light and heat, is what allows life to exist on Earth, and is responsible for many of the coolest phenomena in space. But getting back to our journey to the center of the sun, most of the sun's light is produced in the radiative zone. This region surrounds the sun's core and extends about 70% of the way to the sun's surface. Energy produced in the core takes hundreds of thousands of years to make its way through the radiative zone. This is because the photons of light produced here are constantly being absorbed and re-emitted by the plasma around them. Photons bounce around the radiative zone in random directions for so long that by the time they reach the top of this layer, they no longer have any memory of where or when they were originally emitted. So even though the sun's core is about 140,000 miles away, the light we see coming from the sun actually originates here. Now let's continue our journey to the center of the sun. Below the radiative zone is the convective zone, where energy is transported outward by convection currents of plasma. The plasma here is mostly hydrogen, but it has been mixed so thoroughly that the only elements that remain in their original form are helium and a trace amount of lithium. If we ignore the sun's rotation, the plasma flows up from the bottom of the convective zone, cools as it rises, then falls back down to the bottom after heating up again. These rising and falling currents help transport energy out of the sun's interior and into the radiative zone. Convection currents are also partly responsible for the sunspots and solar flares we sometimes observe. However, because the sun rotates on its axis once every 25 days, the actual flow of plasma is more complicated than this. Plasma near the equator moves faster than plasma at higher latitudes. And as the plasma in the convective zone travels toward the poles, it's deflected by the Earth's magnetic field. The combination of these forces creates a giant dynamo in the sun's outer layers that generates a magnetic field over 20,000 times stronger than Earth's. The magnetic field becomes twisted and tangled as it's carried along with the plasma to the poles. Then it gets released in a massive burst of energy, giving rise to solar flares. Meanwhile, the twisted magnetic field lines that remain anchored to the sun's surface appear as sunspots are not actually darker than the surrounding photospheric plasma, but they do appear darker due to the way our eyes perceive contrast. As our eyes look up at the sun, we see through the convective zone and into the radiative zone, where the plasma is much hotter. Because the plasma is hotter, it emits more light and appears brighter. Sunspots, however, have magnetic fields that prevent plasma from reaching the sun's surface. This means that the plasma in sunspots is cooler than the surrounding environment, making them look dark by comparison. If you ever look at pictures of sunspots, you might notice something strange going on at their edges. You might see faint rings around them, or even multiple rings. These are called umbral or penumbral waves. They are not really waves in the traditional sense, because they do involve a disturbance traveling through space. Instead, Umbral waves are oscillations in the intensity of light coming from the photosphere. There are several different types of these waves, but they all have wavelengths on the order of 10,000 miles, which is comparable to the size of Texas. The waves come in a variety of shapes and sizes, and scientists aren't completely sure how each type forms. But most seem to be associated with the twisting magnetic fields that characterize sun. One theory is that a sudden change in the strength of the magnetic field causes an acoustic wave to travel through the photospheric plasma. It's not entirely clear how this happens, but scientists think that these acoustic waves interfere with each other and with the wave produced by the oscillation of the plasma and sun. The result is a complex pattern of bright and dark rings surrounding sun. We can learn a lot about the properties of sunspots and the magnetic fields that surround them by studying these waves. Scientists can also use them to indirectly measure the speed of sound in the photospheric plasma. Using data from NASA's Solar Dynamics Observatory, researchers analyzed the properties of over 3,000 umbral waves and found that the average sound speed in the photosphere is about 9 miles per second. This brings us to the final layer of the sun, the photosphere. Here, the plasma is cool enough for certain elements to begin emitting light in a way that we can detect. This is why the photosphere is visible to the naked eye and is what gives the sun its characteristic yellow-white color. The word photosphere literally means sphere of light, and it's here where most of the sun's light is emitted. Light from this layer makes up 95% of the radiation that reaches Earth. Below the photosphere is the chromosphere, a thin layer of relatively cool plasma, extending about 10,000 miles above the photosphere. We can only see the chromosphere during a total solar eclipse. At its boundary with the photosphere, the chromosphere has a sharp edge called the chromospheric He2. Beyond that is the outermost layer of the sun's atmosphere, the corona. Unlike the previous layers we've discussed, the corona isn't named for the color of its plasma, but rather for the Latin word meaning crown. It's here where we find the sun's outermost and most mysterious feature, the solar wind. This stream of charged particles flows outward from the sun at speeds of over 400 miles per second. The solar wind is driven by the corona's high temperature, which reaches millions of degrees. This is significantly hotter than the photospheric plasma, but scientists aren't exactly sure why. Most of the sun's light comes from the photosphere, but the corona is still visible to the naked eye during a total solar eclipse. Its fuzzy outline is called the solar limb, and it's here where the sun's magnetic field is carried out into space. Some of these magnetic field lines loop back around and reconnect with the sun, forming a closed loop. Others, however, extend far out into space before connecting to the magnetic field of another star. When a closed loop of magnetic field lines is suddenly destroyed, it releases a burst of plasma into space. This phenomenon is called a solar eruption. Depending on their size and location, solar eruptions can disrupt important communications and power systems on Earth, but they can also produce spectacular auroras at high latitudes. If you want to learn more about our sun or other stars, check out the links below. And thanks for watching!